of the planned schedule. We're on week number 9. So these homeworks 3.1 and 3.2 were being checked off. I'll check off quiz 6 as well. Remember, for the homework, let me bring up my little announcements page. Where'd my announcements page go? I had an announcements page. For your homework, remember, as we're working on these worksheets, you can actually edit it as a Google worksheet if you make a copy of it. Then when you're done with it, download it as a PDF and upload that to Moodle. If you want to finish the worksheet by hand, just print out a hard copy, complete it by hand, and then just send me a picture up to Moodle. You can always print it to PDF and use Edge or a PDF editor and upload that to Moodle. That's what I'm doing with my little stylus pen here. And if you're here in class, all I need to see is your completed work in class. If you have completed some of those, go ahead and you can go back and upload those to Moodle for credit. Remember, the worksheets are part of homework and are part of your grade. So that's what these are. I'm going to be looking at section 3.3 today. So let's pop that up here. I'm going to be talking about inverse functions. Verifying inverse functions. What in the world do they mean by inverse functions? So before talking about the math part, let's just talk about some practical meanings of inverse function. Here's one example of a reversible function. We've got this thing called a reversible heat pump. We don't use them here in the north, and we'll explain why, but in the more mild climates, you can have basically a pump that can work as both a heater and as a air conditioner. As you go in one direction, it takes heat out and provides cooling. When you reverse the pump, the heat pump, it pumps heat into the building and takes out the coolness. Generates heat and heats up your building. So it can be more efficient than an electrical heater. While here in Iowa and the more northern states, electrical heating isn't as cheap as gas heating, so we don't use heat pumps so much in this area. Oh, I'll mark down Miles as having been here. Let me quick get that attendance there for Miles. Welcome, Miles. So there's an example of a reversible function where you have heat. You can heat something, and one side of the motor gets cool. If you run the fan in this direction, you're heating up something that's cold. If you run the fan in the reverse direction, you're cooling off something that's hot. And inside that machine, it can reverse. It can make this part cool or make this part cool. And the part inside the house, you can make the house cool or make the house hot. So there's an example in real life of an inverse function. Basically, you can run in reverse. So doing something in reverse mechanically. Another example of a mechanical reversible function is that wonderful elevator. You hop in it, and it either takes you up or takes you down. The inverse, up or down. That's a very simple mechanical operation. Same thing as like a gear that's winding things up or unwinding. So you wind or you unwind. Some other functions you think of inverse functions. You're driving a car and you get gas needed to go a certain distance. And sometimes you figure out, how far can I go with so many gallons of gas? That would be the inverse function. And I did look up online, if you just go up online and look up inverse function examples. Another example given, when I did a search for this online, let's see here, they gave an example of a sports team. You have players on your sports team, and they have jersey numbers. And they have a name, so you have a name to go with a number on the jersey. Well, sometimes during the season, the sports announcer can't see the name. That's the whole reason they have these numbers. They have the number, and they look up on their chart, and they get the name of the player as they make their announcements. This is a good example because the next year, there may be different players with the same number. So this is only good for a particular season, because the next season, the same number might be given to another player. So the inverse function is good for that particular year. You might think of that as the input, or the range becomes the domain of the number. The players have a number assigned for that season. During that season, that number is identifying a particular player. The next season, if someone else gets that same number, the announcer has to have a new sheet. For one season, that inverse number to a player's name may be valid. There are mechanical type things that, like the heat pump, and you think of it visually as input into one function produces an output y. Well, if there's another function that does just the inverse, takes and does just the inverse of what this function was doing, if I fed that y, that output into that function into this function, I would get x back. This is an example of, if I call this function f of x, and I call this function g of x, or whatever variable I give, happens to be y at this point, this becomes applying g to the function f, or g of the f of x. If I get back x out of the function g, then I know that g is the exact inverse of the function f. And we define that as g of x is then the f inverse of the function f. G does just the inverse of what f was doing. This is the function that we are going to learn about and understand in this section 3.3. You will find sometimes that when you read a book, and if you're like me and you've read it the second time just to try to teach it to somebody else, you may find that in the book there's certain parts are actually easier to understand than other parts. And I find that that's the case with this particular chapter. This chapter, in the way it's written, it starts on some examples and it gets into some harder things, harder concepts with notation that can be confusing. I'm going to jump ahead to the middle of the chapter, which I think is easier to understand. Then we'll come back and see how it all fits together. So I'm going to skip down to the middle of this chapter. Down in the middle of, they give chapter section numbers, down by example 7. I think this is an easier way to understand inverse functions. So I'm going to jump ahead down to the middle of this chapter, and let's see if this makes it easier to understand. I think it's easiest to understand inverse functions when I just think of them as I'm just interchanging x and y. So let's go down there in my notated version. Let's jump all the way down to example 7. Then we'll come back to those others. I'm hoping it will be easier for you to understand this way. Here's what I think is an easier way to understand inverse functions. I simply have a function, like they talked about at the very start, converting Fahrenheit or Celsius. I've given Celsius temperature, or actually given Fahrenheit temperature, I can get Celsius. So I can have F, and using this function, I can figure out what the Celsius. So this is Fahrenheit to Celsius conversion. Well, if I want Celsius to Fahrenheit, all I do is solve in terms of F. So here I have, think of this as a Fahrenheit as a function of some temperature T, or sorry, messed up. Celsius as a function of a temperature is equal to this function, 5/9 quantity F minus 32. But if I want the function, what is Fahrenheit in terms of centigrade input? Well, what do? I just solve that in terms of F. So C equals 5/9 F minus 32. So when I know what my F is, I can figure out C. Well, let's go the other way. In order to have F by itself, well, I need to multiply everything by 9/5. So 9/5 C equals F minus 32. Now I can add 32 to both sides. 9/5 C plus 32 gives me F. Now I have Fahrenheit given centigrade. Therefore, I know this is the inverse function. F, and I can call this F of any input x. I can call this C of any input x, even though I know x is expecting a Fahrenheit temperature. Here, x is a centigrade temperature. If we look mathematically just at the pure numbers, F is the inverse of C. How do I know that? Well, let's do a little more mathematics on that. But remember, all we have done is converted a function where we have C by itself on one side. We just do the algebra to get F by itself on one side, and I have the inverse. This would be, if I put x in there instead of C, 9/5 x plus 32 is the inverse of 5/9 quantity x minus 32. These two functions are inverses. So that's how easy it is. Let's look at this function here. Solve for x in terms of y. That easily can find the inverse of function. You basically interchange x and y
What was the whole one-to-one function thing mean?
Oh, yeah, we'll be looking at that. Yeah, we'll come back to that, the one-to-one. That determines whether this will work. Good question. But assuming we have it, we realize, we discover later on that this only works if we have a one-to-one function. But just interchanging x and y, and then solve again for y by itself equals some function, that will give me the inverse of x. And you are correct. One-to-one, basically, here's a quick answer to one-to-one. One-to-one means I have a one-to-one given an x, there is only one y. Each x gives me only one y. For example, a one-to-one function given any particular x, I know I have a specific y. And I actually didn't write this very good because this quick example does fail the horizontal line test. Here I have this x gives me this y, this x gives me the same y. This is not one-to-one. Here's a better one-to-one. For every value of x, there is only one value of y. That's one-to-one.
And if it was like a circle drawn on the graph, then that would be like a no.
Yep, and a parabolas, they are not one-to-one. One-to-one, unless we say we're only going to look at the parabola on this side of the graph and ignore anything on this side. We can say, okay, a parabola is one-to-one on this side of the parabola. Or you can do the same thing here. You can say, well, it's one-to-one if I throw away this part of the parabola. You have a one-to-one when there is, and you can think of it graphically as, if I have some function and I go from x and I get a y, can I go the other direction? Given a y, do I have a known value for x? Well, if I had the whole range of a parabola, this y, well, I could have gotten that from this x or this x. So a parabola is not one-to-one across the entire range. A parabola, in this particular parabola, is one-to-one for only positive x. So the domain may determine when a function is one-to-one. And that's what we'll be looking back at, the whole one-to-one idea. So when someone gives you a problem, and we can actually find out if it's one-to-one by just trying to solve it in terms of x and y. So for this one, solve for x in terms of y given y is this. So basically, I have this, I want to get y by itself. Well, let's multiply both sides by 3. I get 3y equals x minus 5. Multiply that by 3, that turns into a 1. Multiply y by 3. Now, add 5, 3y plus 5 equals x. There is my solve for x in terms of y. And then, like we saw, once you do that, you just interchange x and y. And I have the inverse function. I have y equals 3x plus 5 is the inverse when f is 1/3 x minus 5. This function is doing the exact inverse of this function. Well,
what would go inside like the parentheses next to the f? Goes in there?
Yeah, we put an x in there. Basically, any variable that goes in there. Let's prove that this is the actual inverse. And here's how you have to prove it. If I take this 1/3 x minus 5. If I feed it to this function, let's see what I get. If I feed this function into this function, let's try that. Y equals 3 times, well, 1/3 x minus 5. And add 5 to it, all right? 3x plus 5. Take that, put that where the x is. What do I get? Well, I get 3 times 1/3, I get x minus 5 plus 5 equals x. So the inverse function gives me back x. So what I see here is I've taken this, actually I'm taking, this is f of x, right? So f of inverse of x, what does it give me? Here's the inverse of x. F of that gives me back x. That's the definition of an inverse function. When I feed the inverse function into the original, I'm going to get back my x. That's proving that this indeed does reverse exactly what this function was doing. And that's the definition. There is one function that will give me back x if I feed it into the original function. That's the definition of the inverse. If it does to its input, that will turn the original function, just feed me back my x. Just like way back at the beginning here, I had that heat pump or some function. I feed it x, some results. I take that result, feed it into the inverse function. If I get x out, then I know that this is the inverse function of x. If I don't get x back by feeding it into this function, then that function is not the inverse. So mathematically, the easiest, I think the easiest way to find the inverse is to do that. Hey, just solve for y, and then you have the inverse. So let's see how I did that again. I said, I have this as y, or this is the current value for y. Let's solve for x, get x by itself. Now let's call x let's call y the input into this. So this, then I can say, well, any input I give it, if I do this to it, I'm going to be doing the inverse of what this function is doing. And to prove that, I feed that function into it, right there. And now the output is equal to x. And I'm trying to remember, did I start recording? Yes, I want to be sure after. Forgot I was, want to be sure I was recording this. Because this can be confusing. And don't be embarrassed if this is confusing the first time. Let's look at it some more. Let's go see how the online book showed me this solution. Actually, they don't show you this solution. Let's see how they show this one. See how we get f by itself and then interchange them left and right. Here is the original function. I have Celsius given some Fahrenheit. I get Fahrenheit by itself, C times 9/5 plus 32, which is what ends up over on this side. And now I've solved for F. If I feed that into the previous function, I see that they actually didn't do the feeding of the reverse. Basically say I get Fahrenheit with this function, or I feed Fahrenheit into this function, I get Celsius. And if I feed Celsius into this function, I get back Fahrenheit. I know that if I feed this as my Celsius, what am I going to get back? I'm going to get back Fahrenheit. And I don't think they actually did that feeding. But that's the essence of inverse function. That what it is doing to x, if I solve for y, or I solve for x by itself, and now call that my output, and call the y my input, then I have the inverse function. We can do this with tables as well. Let's do this with tables. If I have a function given some value of x, I can feed it to f of x and get a value. So f of x, given 1 as its input, I get a 3 out. I get a 2 as its input, I get a 2 out. Well, the inverse function says, well, when I have this as my input, it will go and give me this as its output. When I have this as its input, I get this as its output. So the first function, f of x, is going this way. For this as input, this becomes my output. The inverse function says, well, if this is my input, this will become my output. So given this, the input into the inverse function, we call it f inverse. And remember, this variable here just means I'm representing the input as this variable named y. Whatever this takes as input, if it generates exactly what f of x was taking as input, and generates exactly what, or it takes as in, and the actual same pairs match, his input produces this output, his input produces this output, then they are inverse function. So f of x takes me this direction, given input. This function, taken this as input, is the f inverse. Now, it doesn't matter that we call this one y. Remember, that just says the input into this function will give me this. If that's exactly the reverse of what this function does, then we call that f inverse. The main point here is the easiest way to find the inverse function is just get the other variable by itself. So let's try this one. I'm going to find the inverse function given that as my original function. How do I find f inverse? Let's see, I think I have room here. I solved to try to get this by itself. We'll call this y. So I'll say y equals 2 over x minus 3 plus 4. Well, the first thing I want to do is let's subtract 4 from both sides. Y minus 4 equals 2 over x minus 3. Now let's see here. Knowing some properties of math, I know that if I multiply by x over 3 and divide by y minus 4, I basically can interchange these two. So I know based on this, or I could divide by 2, and then I know the inverse of everything will give me this back on top. I know that this is equal to this if I, well, let's just do the reverse multiplication. I know based on this that x minus 3 is equal to 2 over y minus 4. I'm almost got x by itself. Now I add a 3 to both sides. Now I have solved for x. X equals 2 over y minus 4 plus 3. And now if I interchange x and y after solving for x, my f inverse of x equals, or is defined as y equals 2 over x minus 4 plus 3. Let's see how they explain that in the book by going to that online example here, finding the inverse of that. Let's see their solution, see how they did it. I'm hoping they did very similar to how I did it. Set up the equation, subtract 4 from both sides. There we did the multiply both sides by x minus 3, divide both by y minus 4 to get to there. And now add 3 to both sides, and I have x by itself. And so f inverse of x is that very function. See how I exchanged, made that be, well, that's my input to my inverse function. Doesn't matter whether that letter becomes whatever that letter is. They chose to put x there just because we like to say inverse with naming the input as x. But remember, this variable just means the input into this function, whatever number happens to be there, this is how I calculate a new function. Subtract 4, divide 2 divided by that, and add 3. Whatever the input is, I'm going to do this, is the inverse of whatever the input is for this function to do this to it. I know that this function is the inverse of this one, and vice versa. This function is the inverse of that one. It is commutative. The inverse of one function is the same as that function's inverse. Now, one thing that they introduce here in this inverse idea is domain and range of these two functions. Let's think about this, the domain and range. Remember, if I'm thinking about inverses, I'm taking this function and I'm feeding it to the other function. Well, I know that this function has an illegal value when I have a 3 here. I'm dividing by 0. So this function is 1-to-1, I think, pretty sure, but it has an invalid input at x equals 3. So the domain means all values of x except x is 3. I calculate the inverse function here, and I see that the input to him is all values except where his input is equal to 4, and then I'm dividing by 0 here. So his input, the original function's input, excludes the value of 3. This guy's input excludes the value of 4. And so the domain and range of f, his domain excludes the value of x, and the inverse function cannot have a 4 as its input. Well, how would I ever get 4 out of this input? Well, this would have to be 0, so x would have to be super, super large. So I never actually get all the way to 4 or down to 4. It's always a very large number. Let's see, would I ever get equal to 4? Actually, I might, because this can actually equal -4 at some point. For this to ever to be equal to 4, well, I just know that I can't feed a 4 into here. I'll go ahead and divide it by 0. So the inverse function now has one way of finding it, and I think this is the easiest way. Just like I was showing you, solve for y and you'll find the inverse function. Let's do this one more time using a little more complex functions. How do I solve for y with this one? Remember, this is similar to be saying y, my function, is equal to 2 plus the square root of x minus 4. How would I get x by itself? Well, first, let's subtract 2 from both sides. Now, how do I get x out of the square root part? Well, the only way to do that is to square both sides. Now I can add 4 to both sides. And now interchange x and y. So now f inverse, calling our input x, is equal to, oh, I forgot to add 4 to both sides. Taking x as my input, now calling my input x, inverse, f inverse of x is this. If the original f of x is this. See how I solve for x? Then I say, okay, I'm going to call this my input into the function. And that's the function I can call f inverse. Let's see how the book does that and see if they explain it the same way. They do the quick reverse left and right on you when they get to this step. That's exactly the same steps I just did. Subtract 2. They actually skipped a step here. They subtracted 2, squared it. I like to make that 2 steps. Subtract the 2, then see how squaring it gets you this, and then adding 4 to both sides gets you to here. And then let's talk about the domain again. Remember that this function, his domain, this is the original function, we are not allowing negative numbers in here. So we must have x be 4 to huge positive infinity. And it does include 4, so I put the square brackets. The range is 4 all the way up to infinity. This guy, that means this guy's range then will be 2 up to infinity. His output, if I don't allow anything less than 4, his output is going to be 2 plus 0, 2 plus a larger number, 2 plus a very large number. So 2 all the way up to infinity is his range. That becomes the input into this function. So 2 and larger numbers are only what this function is going to be given as his range, even though this function is happy to take any value of y, because his range is only, his domain is only 4 and larger. That domain of the inverse is going to become 2 and larger. And that's a good thing, because if I took any y, remember, I would be going the other side of that parabola, and that is no longer a one-to-one function. If I have different inputs, I will get 2 sides of the parabola. So that's why this range, to make it a one-to-one, I limit the input of this one, so my inverse can give me the exact input it got. That's the whole idea of, that's why we get the one-to-one issue coming in. Now let's go a little step further here and let's prove that that indeed is the correct answer, that this is the inverse of x. And let's go back there and prove that by feeding this into this. So let's find the inverse. I'll do that. How about I'll do that down here. So if f of x, well, if I want to feed this into the function, I get, or actually, I want to get f of the inverse of the function, x. Here's my inverse of the function, so I want f of x minus 2 squared plus 4. If I take that as his input, let's see what I get. His input goes into this. That means I get 2 plus the square root of x minus 2 squared plus 4. Okay. What do I get there? Well, I get and I forgot to add it or subtract 4 from that. Remember, there's that minus 4. I better put this in parentheses to help me remember. There's my inverse function feeding into my square root. Well, look at that, the 4 and the minus 4. The 4 minus 4 cancel out. Well, I know the square root of this is 2 plus x minus 2. And look at that, what I get for output equals x. So the inverse fed into the original function gives me back x. That is the check that that indeed is the correct f inverse. And that's something we're going to be doing regularly as we think about this inverse function. Now let's go back to, let's see if we do the graphs. Yeah, let's do the graphs now, and then we'll come back to the beginning of that chapter, because I think the beginning is actually the harder things to understand. Let's look at the graphing part now. Take a little breath here. We've done some math, and we've done solve for x in terms of y. Now let's just think graphically. If I have a function like this, I have an input, and the function gives me this output. So it lands on the graph, and the graph shows me what y I get as a result of that particular x. Any input, I find what its output is. I find the input, I go see what that function generates, and I read that value. That's f of x. Going the other direction is my inverse. If I have this as my output, going this direction, finding out, well, what x gave me that value, that's the inverse of x. Or if you want to say, well, y is my input, or f of x is my input, I find out I got a 4, going that direction. So f inverse, just think of, I'm figuring out, well, what value of y was produced by what value of x? And you can see that if I had this as a parabola, not 1 to 1, I wouldn't know which value of x got me to 4. So therefore, for a function to have a value, a known value, my function then therefore needs to be 1 to 1. I can't have two possible values of x giving me the same y. That is where the 1 to 1 function is important to check, because without 1 to 1-ness, I don't have an inverse. So therefore, 1 to 1 required for f. If I'm able to find f inverse, I must have a 1 to 1 function. Otherwise, I don't know. And mathematically, I can't solve for, if I have a 4, where did it come from? Would the 4 come from this value of x? Or did the 4 come from this value of x? That would not be 1 to 1. Therefore, I can't do I can't do 1 to 1. I can't do f inverse if I don't have 1 to 1-ness. And we can see that on the graph with that simple horizontal test. If I do a horizontal line through my function, if I get one crossing, then I know I have a 1 to 1 function. And here's an example of the square root. And you can think of the square root as basically the inverse of the square. It is one. If we look at the square just going in positive x, it is 1 to 1. So therefore, square root, the positive square root of any number x means I'm throwing away that as the result. The positive square root is the inverse of x squared when x is greater than or equal to 0. Square root of x, the positive square root, is the inverse of x squared. And when we see that relationship, as we start to draw it on a graph, we'll actually see, hey, all we're doing is reflecting it around this y equals x diagonal line. If I can reflect my function around that diagonal line, that is the graph of my inverse. And of course, that only works with 1 to 1 functions. So here's an example here. I have a function. They didn't even give me what the actual mathematical value is. They just show me graphically what is my function. Well, just think of putting a mirror right here on the diagonal line. And I know the mirror of that is that. Let's see, and I'm hitting 4 there, so that's a mirror there. And this follows the vertical line, so that means this would follow the horizontal line here. So I can see that the reflection around that diagonal line would be something like that. And let's see their solution, see if they did better. There is the inverse. Basically reflecting it around. Another way to think of it is flipping our page over and seeing inverse displayed on the back side. So reflecting it around that diagonal line gives us our inverse. let's see, did we give an example 8? Where's example 8? Here's figure 8. Where's example 8? Figure 7. Oh, I'd have to graph this. Won't worry about that. Now, before we go on and go back to the, look at this some more. Anyone have any questions about that? Should I just go through it again? Let's see here. Well, let's take a look at the worksheet. Let's start on that worksheet 3.3. Let me bring that worksheet 3.3 up. Kind of helps us to look at it in a slightly different way. Here's worksheet 3.3. First of all, we just want to see, are they one-to-one functions? Let's just worry about the one-to-oneness, and then we'll think about inverses. Which one of these are one-to-one? Remember, the test for one-to-one is simply the horizontal line. Do I get one value of y given a specific x? Or is there another value of x that will give me that same y? This one, horizontal line test. If you think about this, you realize that for a function to have inverse and for the inverse function to be valid, basically, I need to pass both the horizontal and vertical line test. The horizontal line test is a quick way to see one-to-oneness. We see that this one does not pass either of them. Vertical line hits twice, and a horizontal line hits twice. It is not one-to-one. This one, a horizontal line test passes, and the vertical line test passes. This is one-to-one. Same thing with this one, horizontal line. Because of the way this is defined, I am not defining my function. The range, or the domain of this function is -1 all the way up to infinity. That's my domain. I see that its range is, well, it looks like -infinity all the way up to and including 1. If someone asked me to analyze it more deeply, to know whether it's one-to-one, all I do is a horizontal line test. Only one crossing. So that is one-to-one. This, any linear function, except for an actual horizontal line, is one-to-one. Again, a one-to-one here. If I want to examine the domain and range, this one, it's a little unclear whether the inverse is one-to-one right there, but I'm pretty sure that it doesn't have a completely vertical there. Horizontal line test passes everywhere, one-to-one. This guy here, sorry, I get two different x's give me the same y, not one-to-one. If I said, let's only examine this function between the values of where it crosses here and where just before it crosses here, or actually just before it crosses here, it is not one-to-one there. I could say, well, it is one-to-one between here and here. But it's not one-to-one across all values of x. So when you see a function that is repeating like this or cyclic, you say, well, let's examine just one area of it. We'll say it's one-to-one in this area, which it is. And if we want to examine it in a different way, I can find it is one-to-one there to there. And I can do a separate mathematical analysis between those two values and do all the fun things I can do with inverse. But I have to say, all the math I do when I'm examining the inverse is only valid in a specific range where it is one-to-one. Anything beyond that range, nope, it's not 1-to-1 for all x. Now we get back to that part about if I have a table of numbers, not even knowing what the function is. Well, let's go back now and look at the table form of inverse functions. And this is where I can go back to towards the, let's see, or do they give me tabular down here? You can go back towards the top of the chapter. Yeah, let's go back to the top now. And let's think about the tabular view of this. If I have a table of numbers, given an input t, I have some result. So my function f, which happens to be give me miles. When you give me minutes, I'll give you miles. I get miles as my output. What does inverse f mean? Well, let's see here. So many minutes, I know I can travel this many miles. So minutes given minutes, and I will determine or calculate miles. F of -1, well, let's see here. That means what value of minutes gave me 70 miles? F -1 of 70. Actually, F -1 of 70 means the input was 70. What was the output? Well, what does this function mean? How long will it take me to go 70 miles? So the inverse function is, well, let's first set our initial function is how far can I go in t minutes? That's the question the function is answering. Given so many minutes, how far can I go in that many minutes? The inverse function is asking, how long will it take me to go that many miles? The inverse is how much time does it take to go so many miles, m miles. That's the interpretation of F inverse. How long to go 70 miles? Well, the answer is 90 minutes. But you can see how given 30 or given 90, I get 70 minutes. I can get the inverse of, well, how long does it take me to go 70 miles? The answer is 90. Let's see how they explain it, just to get another viewpoint. Just like what you should be doing when you are thinking through these problems. If you have a hard time understanding what they're saying here, take a look at a YouTube video on that topic. Let's see how they explain it. The inverse takes an output of f, returns an input for f. Inverse f inverse of 70 is the output, which is miles, 70 miles. The inverse will be, how long did it take me to go that 70 miles? So to drive 70 miles as my input to inverse, it takes 90 minutes. I think I actually like my explanation a little more because I turned it into a question. How far can I go in t minutes? The inverse question is, how long does it take to go so many miles? How many miles can I go in t minutes? Inverse, how long does it take me to go that many miles? And if I have a table, it's just a matter of finding the output of the original function. And remember, the original function output is that. And usually your table is written where the input is the top row. That is my output of the original function. And then going this direction, taking this as input and going this direction is my F inverse. And whatever this value is, we still, remember, this is probably the most confusing part. We still put an X in there. But remember, that variable X just means what that function takes as input takes me exactly the reverse direction, the reverse calculation of this function. This function took t as input. F inverse is whatever I have for output from f of t, I get the exact inverse from my the f inverse function. If it helps, when you think of these word problems, put it in a word question. How far can I go in so many minutes? The inverse is, okay, how many minutes does it take if I have gone this many miles? And I'll get the inverse. So now let's look at that worksheet given a table. Even without a table, I know that if f of 5 equals 8, given an input 5, I get an output of 8. This is my f. I know that the inverse function, if it takes that as input, just like my little beginning diagrams, f of inverse of input is going to give me back my original x. So if I take 8, feed it into f of f inverse, I know that this is going to feed me out a 5. Because remember, f inverse will take me out exactly to what I had fed as input into f of x. So I know f of 5 gives me 8. F inverse of 8, I know will give me 5. It will go exact inverse. So my table will just be the matching pair reversed. Same thing with here. If I feed it -8 and I get -4 into the inverse function, well, I know that f of -4 will give me the -8. And again, this is all assuming that f is 1-to-1. If f is not 1-to-1, then I can't know for sure. But they did tell me, yes, they are 1-to-1. These rules are obeyed when it's a 1-to-1 function. But f must be 1-to-1 in order for me to be able to say that. Now I have a table, f of x. And I know any input of x into my function, y is the same as f of x. Well, the inverse table for f inverse for his input, well, if this is my input, well, it's simply the reverse table. My input into my f inverse is 1, 4, 9, 13, 15. His output is going to be exactly the inverse. So now I know f inverse of any of these inputs gives me exactly what I originally had. Because we all know the rule is f given the result of f inverse of any input is going to be equal to x. It's going to reverse what this did. I'll get x back. And I get the same thing this way. Applying f inverse to the output of f of x will get me back x. That's the definition of what the inverse function has to do. Oh, I forgot to put -1 there. F inverse reverses what the original function did, giving me back my x. And of course, following all the rules that along the way, I'm not dividing by 0. Going back to our easy way to solve for an inverse function, remember, I just treat this as y equals 2x plus 9. We want to get x by itself. Subtract 9 from both sides. Now divide by 2 so I can get x by itself. Now just reversing the roles or the positions of our x and y, the inverse function, f inverse, calling its input x, is equal to x minus 9 divided by 2. When I take that as my input, I'll get back my x. Okay, so whenever I have an input, I do this to it, subtract 9 from it and divide by 2. That is f inverse given f is this. So the answer here would be x minus 9 divided by 2. Now, just for some practice here, let's see that this will work. Let's figure out f inverse of my function f of x to prove that we got the right f of x, or f inverse. Okay, so let's take 2x plus 9 and feed it into this function. So I'll do f inverse of 2x plus 9. What does that give me? Equals 2x plus 9 minus 9 divided by 2. We see that the 9 cancels out. And I get 2x divided by 2 equals x. Showing me that, yes, indeed, I should, and I do get f inverse of the original functions give me x. Now, just to practice this, let's go the opposite. Let's show that f of f inverse of x. What does that give me? That better give me x. Well, what would that be? Well, 2x plus 9 becomes 2 times this plus 9. 2 times something divided by 2 gives me x minus 9 plus 9. Showing that f inverse, or f of f inverse, gives me back x. That's my check. Yes, I got the right answer. Are you finding it a little more understandable here? Let me know if you maybe go over anything. I'm thinking just going through these, practicing by hand here. This one here. Remember, we just do the solve for the x by itself, we'll make it easy, put a y there, equals 1 over x plus 14. Remember, I can multiply by x plus 14, divide by y, or I get x plus 14 equals 1 over y. Now I subtract 14, x equals 1 over y minus 14. Now interchange x and y. F inverse of x equals 1 over x minus 14. And remember that x just means, given an input, here's the number I calculate based on my input. That is doing just the opposite, the inverse of dividing by that number plus 14. Let's just show that just by practice. 1 over x minus 14 plus 14. See how I get 1 over x when the 14s cancel out, and 1 over x equals x. So now I know that is the correct answer. I feed 1 over x minus 14 to where x was, getting x back. So, better get the right answer here. There's my answer right there, so I'll put it right in the proper place. 1 over x minus 14. And I think we'll stop there. I'll give you a chance to think about these as we'll get next time. We'll do more complicated inverse functions. And I'm hoping that jumping to the middle of the chapter, I'm hoping that has made it, I'm hoping, easier to understand. For me, it made more sense to me to jump to the, hey, just invert the x and y, and things, it just seems so much easier to figure out the inverse of x. Start thinking about this at the start. This part can, I'd say, get very confusing and get you to kind of fog over. But if you think about it this way first, that all we're doing is solving in terms of y. Where did that statement go? Oh, it was after example 6. Yeah. You just solve it in terms, or basically solve for x and then interchange x and y. To me, that is, for me, that was a breakthrough, making it so much easier to understand. All we're doing is putting y by itself, or putting x by itself, that becomes my inverse. Here, I get f by itself, and I figure out the inverse. Any function, get the x by itself by doing your algebra, and you figured out the inverse. All right, we'll stop there. We'll see you on Thursday. Send any questions in email. I'll be happy to try to help you out. And this is also recorded. You can always go back and review that.
Quick question.